Alrighty, so let's talk about the accuracy of chronographs. How accurate is your chronograph? And well, how do you know if it's actually accurate or not? Yes, you can compare it to other ones, but are they known to be accurate or not? You can compare it to multiples. You're probably going to get a good enough idea, but what does good enough mean? Within what sort of level of accuracy can you actually be certain? So we'll talk about how the chronographs work, and then we'll talk about how you get errors and different sorts of issues around that. So we'll talk about the optical style of chronographs, which is what the NateChrony is. So there is a sensor at the start and another sensor. It'll detect the pellet when it hits the first sensor, starts timing, hits the second sensor, stops timing, distance over time, there's your speed. We won't go into radars. They're a very, very different type of measurement system, but anything that has sort of two sensors, infrared, light, the sunscreen, the shoot through things, that's fundamentally how they work. Now, in terms of the amount of errors and things like uncertainty, the first is going to be the physical dimensions. What is the distance between those two sensors and how accurately is that known? If you're talking about something that is, just punched out en masses in a factory, how accurate are they actually manufacturing those devices? You talk about a fine swish watch. We're dealing with things well under a millionth of a second. The alignment and how things are constructed is just incredibly important to ensuring that you get accuracy at the end. The second is going to be the timing, is how accurate can you count the time between those two sensors. There's some other things, programming software, that really help with the accuracy. I'm not going to go into those. They're a bit proprietary. So in terms of the physical dimensions, can you use just a good set of calipers to be able to measure the distance between the sensors? How accurate are these? When were they last calibrated? And things like temperature. These are made from metal. Metal expands over temperature, so that you will get different results depending upon the temperature. So I can announce that the NateChrony now has some certification, some calibration behind it. We worked with the Australian National Measurements Institute. This is the official government institute that regulates and does all the work regarding the measurements system in Australia. So everything is traceable back to the international units of measurement. So we sent some devices off, we got them to perform measurements. We now have what we consider master chronographs that have known dimensional accuracy within certain tolerances. We have multiple of those, so we can then test everything from a physical perspective of a known master chronograph. So that's excellent. We can, as I said, we can now look at some really fine accuracy and some good solid results because we know the dimensions of those. I mentioned before, if they're not constructed well, then you're going to get differences in the alignment. What sort of difference really matters? If we're talking a tenth of a millimeter, that's going to be about 2 feet per second at 1,000 feet per second of something that's roughly this big. So you can bring them closer, or maybe you want to take them wide apart so that you've got a better tolerance because the dimensions are further apart. If they're further apart, a device that sort of folds open to get a really big distance between sensors, your pellet's going to decelerate over time. So what you measure at the muzzle is kind of not what you measure 300 millimeters away. So that's a really interesting thing as well. If you've got something that's opening up, you've got a hinge, you've got some movement, some play, maybe that's going to wear over time. And if that's made out of metal, metal expands when it gets hot. So on a cold day, you will definitely get different readings than on a hot day, purely because the metal has expanded and those two sensors are different spacings apart on different days. So the calibration was all done at around 19.7 to 20.3 degrees Celsius to account for thermal expansion of our devices. We now have a good known distance between that. Also, our assembly procedures are very specific so we can maintain consistency. But at the end of the day, we'll install a special adapter on the Master Chrony. Every single NateChrony is then going to be calibrated from the master chronographs when we get them back this week. We can also do cool things like put them the other way and see how much pellets are decelerating within the first 100 to 200 millimeters of travel. we've seen some consistent results, and it's really interesting that, yeah, you can definitely detect pellet deceleration within 100 millimeters of travel purely by mounting two accurate known chronographs back to back. So that was a really interesting thing. We may publish a video around that shortly. So that's a physical aspect of it. As long as you've got good known dimensions, you can sort of take that sort of level of uncertainty or issues, inaccuracies out of that measurement. Let's have a look at timing. Timing's an interesting one. If we have a look at time on the x-axis, what the chronographs basically do is check for a pellet. So do I have a pellet? No. Do I have a pellet now? No. Do I have a pellet now? Yes. So when did the pellet arrive? Did it arrive right then? Maybe it arrived here. Maybe it arrived here. You don't actually know because there is a time difference between when you were reading the sensors and trying to detect the pellet. That's what's called uncertainty. You don't know when the pellet actually arrived. So the trick with that is to get these measurements as close as possible and also to take more shots. With more shots, that should average out, but then your spread could be really, really bad. In terms of the timing accuracy of the NateChrony, we're within about 0.2 to 0.3 of a foot per second. So we've got our timing extremely accurate. Other things that we do from a programming perspective to make sure that we're getting really, really good accuracy around the timing aspects of that. In terms of how accurate is the timing, if you've got 1 microsecond, that is a millionth of a second. That is actually going to be 4 foot per second at 1,000 feet per second. So that's not that great. A millionth of a second actually does not cut it when we're talking about chronographs and some significant speeds. If you then want to add in top your measurements as well, something like a tenth of a millimeter, 4 feet per second, a microsecond, sorry, a tenth of a millimeter, 2 feet per second, add in 4 feet per second if you're a microsecond off, you may not be able to get within 10 feet per second of an accurate measurement at 1,000 feet per second, which is not that great. If we talk about averages, well, okay, to worry about that, I'll just take lots of shots. Well, if you've got 10 shots that are 10 feet per second high and 10 shots that are 10 feet per second low, the average works out, but then you've got a spread of 20 feet per second. Is that spread your pellets? Is it your firearm? Or is it the timing? You don't know. So you'll get an accurate measurement from the speed, but the spread could be well out. So that's what we wanted to make sure that we continue to push a lot with the NateChrony, is so that you can rely on the speed, but you can also rely on its accuracy and consistency in terms of the spread. You can rely on every single result out of the NateChrony. You don't have to take 10 shots and wonder, is it really performing well? So how do you add this up and what does it all mean? With the measurements, they're accurate to about 0.04, 400ths of a foot per second. 400ths of a millimeter. And then we've got the timing. I won't talk too much about the timing. There's specific ways in which you add up uncertainty in metrology, root mean squared, all sorts of formulas. I'll take the worst case scenario, the maximum physical issue, uncertainty and errors, adding that up to the maximum uncertainty of timing. And the NateChrony is less than 1 foot per second at 1,000 feet per second. So absolute worst case, 1 foot per second at 1,000. Realistically, we're probably around about half a foot per second. So every single shot you take, it's going to get measured. It's going to get measured accurately. You can rely on our readings, the speed readings, because we've got the certification behind it. And you can also rely on things like the calculated standard deviation and spread, because we've worked on that as well. So that's the NateChrony. As I said, after we get the master chronographs back, every single NateChrony will be calibrated from a master chronograph so that you can be sure when you're actually doing your testing, you are getting accurate results each and every time. So hopefully that helps get some understanding about accuracy in chronographs and also just help you understand a little bit more about the efforts we go to for the NateChrony in terms of its accuracy. Enjoy your testing.